of processes. ठीक है. Or essentially thermodynamics की applications are about interconversion of heat and work. So we can actually jump to a really nice question, which is, I believe, also uploaded on the Google Drive link. Um, which is not this one at all. Let's see this one. ठीक है, and let's just solve the entire question from scratch. Honestly, क्या फर्क पड़ता है on our board. The question was कि um, हमने एक thermodynamic cycle है हमारे पास, पूरा cycle. ठीक है. The first process is an isothermal compression from P1 is equal to 100 kilopascal, V1 is equal to 1 meter cube, to P2 is 500 kilopascal. और इसके बाद वाले दो प्रोसेस are simply put, उसके बारे में सिर्फ ये लिखा हुआ है कि they are an isomeric process followed by an isochoric process, but the cycle is now complete. And what we want to do is we have to find the work done for all processes, the heat transfer for all processes, the overall work done, and efficiency पे हमने बात नहीं की, मगर इसी example के जो है ना देखते हुए ही हम efficiency पे directly बात करेंगे. And also find the temperature at all points given that the mass of air is 1 kilogram. ठीक है. So first thing we need to do is draw the PV diagram for this entire process. ठीक है. Remember that एक process 1 से 2 में the area under that line, right, is the work done for that process 1 से 2. But there are now other processes. We've got processes 2 से 3 and 3 से 1. So 3 processes now. ठीक है. So before we draw it, and if you don't have a lot of experience with like solving problems, you wouldn't know where to begin, sort of, right? But like it might be seem kind of not very obvious कि मैं जहाँ से points शुरू कर रहा हूँ और खत्म कर रहा हूँ वहाँ पे क्यों खत्म और शुरू कर रहा हूँ, but उम्मीद है कि clear हो जाएगा. So the first process is a compression process, right? um हमारे पास originally pressure let's say 100 kilopascal था point 1 पे, and then we increased it 5 times to maybe around 500 kilopascal. And please don't look at the scales, this is not to scale, obviously ये तकरीबन 3 गुना है मुश्किल से, but whatever. ठीक है. So originally my volume was 1 meter cube. ठीक है, without doing any math, so my point 1 is right around here. Without doing any math, it's clear enough कि जब मैं pressure बढ़ाऊंगा तो मेरा volume कम होगा in the compression process. ठीक है. So as I increase the pressure, मेरे ख्याल में I said something very weird. I didn't say कि मैं pressure बढ़ाऊंगा, but whatever. When I increase the pressure, when I compress this thing, the volume is definitely going to decrease. ठीक है. The volume at this point 2 is definitely going to be lower. ठीक है. So you got state 1, state 2, and an arrow. You need all three. उसके बाद वाले दो processes के बारे में honestly there should be more information. It's a bit confusing the way this problem is stated, but it's just an example problem. But still, the idea is that process 2 से 3 is an isobaric process, which means that the pressure is constant. ठीक है. So it has to follow somewhere around this line, constant pressure वाली line. And ये भी बताया गया कि it's expansion. सिर्फ isobaric नहीं लिखा हुआ, expansion भी लिखा हुआ है. So wonderful. We can rule out this side and we can say that since it's expanding, it actually has to be on the right side. It has to be moving that way. ठीक है. हमें नहीं पता कि कहाँ तक expand करे, but it is expanding. और उसके बाद वाला जो process है 3 से 1, that is an isochoric process. So isochoric, you might remember, was constant volume, and it ends at 1. So since this process ends at 1, safe enough to say कि constant volume process है, 1 पे end हो रहा है, तो it has to be somewhere along this line. प्रेशर कम हो रहा है, ज़्यादा हो रहा है, हमें पता नहीं है, but still. ठीक है. So ये थोड़ा सा गंदा सवाल था, honestly, हम मुझे direct values दे देनी चाहिए थी. But the only way this is possible is if point 3 is over here, and first process 2 say 3 is a constant pressure expansion, and then 3 to 1 is a constant volume process. ठीक है? This is the only way this is possible. So now I've got my 3 processes. जो पहला process है 1 से 2, उसमें the area under the curve represents the work done for the process 1 से 2, marked in yellow. जो दूसरा process है उसमें the area under the curve actually is this entire thing. ठीक है? And then we are going to see later on that for the entire cycle, the area enclosed in this curve, right? ये जो area है, enclosed in this curve. My God, I've created a mess. This is the only, this is the net work done for this entire cycle. We're going to see that much later. So I'm just going to undo all of this for now. ठीक है? So पहला step is often just finding out all of the states. All we know so far is कि 1 पे हमें pressure पता है जो कि है 100 किलो पास्कल, टेम्परेचर भी नहीं पता हमें, और वॉल्यूम पता है जो कि 1 meter cube है. But we also know that the mass of the air is 1 kg. So you can actually also draw this diagram in peak small v if you want. There's no difference between small v and capital V because mass is 1 kg. So this is 1 meter cube or 1 meter cube per kg, right? Because 1 kg की बात हो रही है. Temperature भी हमें नहीं पता. So it's useful to find temperatures, volumes, and pressures pretty much at all points. We're going to start with that. ठीक है? Point 2 पे the only thing that we know is कि 500 kilopascal pressure है. ना हमें temperature पता है, ना हमें volume पता है. ठीक है? और point 3 पे फिलहाल तो हमें pretty much कुछ नहीं पता. ठीक है? So let's start by finding whatever is unknown. Can we start by finding temperature at 1? How would we do that?
Sir, PV is equal to MRT.
Right, so T comes out to be P1 V1 over MR. ठीक है? So units are really important. We are talking about air now. The way I would use ideal gas law is कि जो R की value है ना, I think we may have done this. I'm not sure. किसी एक syndicate के साथ किया था. R is the universal gas constant divided by the molecular weight. ठीक है? Which you can actually calculate as well. K it was 8.314. The RU जो था kilojoules per kilomole Kelvin divided by तकरीबन 29 kilogram per kilomole. So this came out to be 0.287 kilojoules per kg. Or this might be a good enough time, I suppose, to introduce the tables, which is also uploaded to the same EA folder. So these tables have a lot of values जो कि आपको बार बार retrieve करनी पड़ सकती हैं for a lot of stuff. The thing that we need right now is from ये एक table on properties of ideal gases, which is way down, table 820. ठीक है. Honestly, R के case में R is a constant, so you don't even need to tabulate it. ऊपर कहीं है? ऊपर भी कहीं नहीं है. But um, the thing is that R is just the difference between CP and CV, right? But I'm gonna keep this open because we might need this again in a bit. So the value, this 0.287 is also equal to the value of CP minus CV, जो कि आप table से भी देख सकते हैं in case you don't remember this value or any of this stuff, which was 0.007 minus 0.718 I believe, जो कि उतना ही आ जाता था. ठीक है. So in any case, you can find R, I hope, or you would remember it. ठीक है. The difference between these two is actually equal to R. The ratio between these two, Cp divided by Cv, 1.005 divided by 0.318 is equal to K, which is the ratio of specific heats. This is what I was talking about earlier. So anyway, ideal gas law हम use कर रहे थे. ये इस पे बेके करके अगर values डालें, pressure at 0.1 is 100 kilopascal. Multiplied by volume at 0.1 is 1 meter cube, divided by mass is 1 kg, right here, and the gas constant is uh, 0.287 kilojoules per kg Kelvin. यहाँ पे Kelvin भी होना चाहिए था. ठीक है. So can I just crunch the numbers or do I need to do any unit conversion? अच्छा, ये already क्या कहते हैं सॉल्व्ड है, सो मैं नंबर्स जो है ना वहीं से उठा लूंगा डायरेक्टली. कैलकुलेशंस जो है ना. Do I need to convert anything? What do you guys think?
Set kilopascals into pascals.
Okay, so that is the probably the most sensible guess, but the problem there is कि अगर मैं इसको चलो कर सकता हूँ, but then I also need to convert this 0.287 into joules per kilogram Kelvin. ठीक है. So either convert them both or convert neither. ये भी किलो है, ये भी किलो है. ठीक है. And everything else is just proper SI. So it just works out on its own. या तो इसको भी 100,000 लिखें और फिर इसको 287 लिखें. ठीक है. So this is totally fine on its own. The unit that you're going to get at the end of the day is Kelvin, right? So this comes out to be 348.4 Kelvin. You can verify my calculations because if it's different, that means मैंने कुछ यहाँ पे गलत लिखा है. ठीक है. The problem is already solved. It's already uploaded on the Google Drive. So that means कि अगर मैं इसे Celsius पे convert करना होगा तो it's around 74.5 Celsius. ठीक है. So that's temperature at 0.1. उसके बाद वाले जो काम है ना वो it's really easy. Temperature at 0.2 is actually इस स्टेटमेंट से हम टेम्परेचर एट 0.2 के बारे में कोई बात कर सकते हैं. पहली स्टेटमेंट प्रोसेस 1 से 2.
Yes, so we can find the volume of the state 2 and also the temperature.
ठीक है. सो वॉल्यूम किस तरह निकालेंगे?
Sir, Boyle's law.
यार मुझे याद नहीं है बॉयल्स वाली कौन सी थी, चार्ल्स लॉ
So
कौन सी थी.
P1
हम
V1 is
सिर्फ
equal to
आइडियल.
P2. P1 V1 is equal to P2 V2 because it's an isothermal process.
ठीक है. अब सिर्फ आइडियल गैस लॉ है, अब बॉल्स और चार्ल्स नहीं है. सो इफ दिस इज इक्वल एंड इट्स एन आइसोथर्मल प्रोसेस, दैट मींस के V2 is just going to be equal to V1. In fact, let's just call it चलो V1 multiplied by P1 over P2. right? And the beautiful thing about writing equations like this is because आपको units का ख्याल नहीं करना पड़ता, because pressure is just a ratio now. So that means कि really अगर pressure 5 गुना बढ़ गया है तो volume 5 गुना कम होगा. It's as simple as that, but obviously there are numbers involved, so you can write it as 1 multiplied by 100 divided by 500 meter cube, which means kV2 is 0.2 meter cube. ठीक है, so ये जो V2 था ये यहाँ पे 0.2 मीटर क्यूब आ गया, और टेम्परेचर जो है, टेम्परेचर कितना होगा?
सर वो सेम होगा 74.5 डिग्री
Yes, so
सेल्सियस।
let's just keep everything in Kelvin. वैसे तो you're right, absolutely right कि 74.5 मैंने भी convert किया हुआ है because that's what we are used to. But like आदत डालना आहिस्ता आहिस्ता में शुरू करना है of writing and thinking in Kelvin. ठीक है? So yeah, temperature at 0.2 is the same as the temperature at 0.1. Then moving on to 0.3. 0.3 पे pressure कितना है?
500.
सर 500 के।
So the pressure is the same as it was at 1, sorry, at 2, which is the same 500 kilopascal. Volume कितना है?
So
सर
1 meter cube.
The same as it was at 1.1 पे और 0.3 पे volume same है. So it's just 1 meter cube. और temperature actually थोड़ा सा calculate करना पड़ेगा, मगर बहुत ही ज़्यादा सादा calculation है. कोई मुझे directly मुझे बता सकता है कि क्या multiplied by क्या होना चाहिए?
सर 500 डिवाइडेड बाय 0.287।
ठीक है, सही है, बिल्कुल सही है. So it's if you use the ideal gas law, if you look at this equation जो कि यहाँ पे नीचे लिखी हुई है, right, and you use it again, shouldn't have done that. The only thing that has changed is 0.3 पे, so T3 is going to be equal to P3V3 divided by MR. The only thing that has changed is कि ये जो है ना 500 हो गया instead of 100. ठीक है, so you could reapply the ideal gas law, or you can just multiply this 348.4 into 5, same thing, right? So that's the बाकी ideal gas law में कोई change नहीं आया. So this 348.4 multiplied by 5 comes out to be, should have changed the color, 1742 Kelvin, यानी कि तकरीबन 1470 सेंटीग्रेड. ठीक है, so we are finally done with calculating all of the states. 1 2 3 तीनों states पे pressure, volume, temperature हमें तीनों चीजें पता चल गई हैं. ठीक है, so now we can do some other calculations and have some more same, I don't want to say that, but we're gonna have more fun by calculating things in multiple different ways. ठीक है, so for this process 1 से 2, for this process 1 से 2, what's the work done? How do you find it?
सर पीवी।
Area under the PV diagram, which for an isothermal process, let me just open up एक slide जिसमें ये जो हमने कुछ calculations की थी ना, उनकी एक summary थी, which is this slide right here. ठीक है, अगर process ये इस टाइप का हो, PV raised to the power n is equal to constant टाइप का प्रोसेस हो, अगर उसमें n 0 हो तो constant pressure प्रोसेस होता है, तो उसमें वर्क डन जो होता है that is P into V2 minus V1. अगर n 1 हो तो that's a constant temperature process, isothermal process, in which the work done is V1 V1 times the natural log of V2 over V1. And if it's neither, then you can just use P2 V2 minus P1 V1 divided by 1 minus n. ठीक है. So यहाँ पे जो हमारा process 1 से 2 था, that was an isothermal process, in which you use this equation in the center, right? So the work done for process 1 से 2 is P1 V1 natural log of V2 over V1, right? अच्छा, अब अगर मैं यहाँ पे P1 को लिखूं 100 because it's 100 kilopascal और V1 को लिखूं 1 मीटर क्यूब, और नेचुरल लॉग के अंदर तो रेशो है ना, क्योंकि नेचुरल लॉग के अंदर रेशो है, इट रियली डजंट मैटर, सो दैट रेशो इज जस्ट 0.2 divided by 1. ठीक है, the only thing that matters is कि if you take a negative, sorry, if you take a natural log of a fraction, what do you get?
Negative number.
And if you take a natural log of 1,
0.
right? Um, तो 1 basically means कि volume का change ही कोई नहीं हुआ ना. So in that case, वैसे by the way, this is not the right equation to use for that, but still, so यहाँ पे जो है ना, the only statement इसकी वजह से ना, इस natural log में fraction होने की वजह से this is going to become a negative number. ठीक है. मगर इसके units क्या हैं overall? Any
Sir,
ideas?
working units.
Joules,
Working units.
Newton meter,
Yes.
BTU, वर्ग के बहुत सारे units होते हैं.
Sir, Pascal's meter cube.
किलो भी तो है ना, right? So Pascal is SI,
CT.
meter cube is SI. So Pascal into meter cube actually is not the right way of saying it. You want to probably call it a joule. But since there's a kilo involved here, you get kilojoules, right? So Isaroka product has units of kilojoules. Okay? Of course, these are work units, so correctly pointed out there. And its value comes out to be just minus 160.9 kilojoules. Okay? So that is work done for this process 1 or 2. What about work done for the process 2 to 3? An even easier calculation.
Sir, 500 bracket 1 meter minus 0.2.
Okay. So the only thing worth considering here is which is a question that you must ask, is कि 1 minus 0.2 होगा या 0.2 minus 1 होगा. ठीक है. And its final value minus initial value, right? So this is fine. और इसके नतीजे में the answer that you're going to get is 500 times 0.8, so 400, मगर units क्या होंगे? Same as before, right? So this is once again in kilopascal, and this is once again in meter cube. So you're once again going to get kilojoules. And finally, what is the work done for process 3 to 1?
Sir, 0 kilojoule.
Yeah, it's just 0 because he is isochoric, no volume change, no PDV work. Okay? So that means if you do all 3 of these, one after the other, and you get a cycle, then the overall work done is just the sum of all 3 of these. Okay? So that's just 160.9 plus 400 plus 0, right? Which is 239.1 kilojoules, which basically means that even though, I mean, this is totally unrealistic and this is really bad, this is basically an engine of some sort. ठीक है? अगर आप ये 3 processes one after the other करो, you're going to get a net positive work output of 239.1 kilojoules, right? and you can repeat them over and over again. ये अब अच्छा सवाल है कि how do you actually manage that? How would you actually manage to do isothermal compression, and then how do you manage to do isobaric expansion, and like constant volume पे ये जो heat वो हो रही है, heat removal हो रही है. How do you manage to do that? That's a different question. Is it practical or not? That's a different question. It's not very efficient, जो कि हम अभी पता लगाएंगे कि efficient नहीं है, but it is at least a heat engine, right? It's going to produce some positive work output. ठीक है? So work done हो गए. Next step, try to find the work done हो गए heat transfer. So next step is that we try to find the heat transfer for all of these processes. ठीक है? So first of all, for process 1 से 2, so heat transfer निकालने के लिए we're gonna have to invoke the first law of thermodynamics, which is delta U is equal to Q12 minus W12. ठीक है? The question is, for an isothermal process, will there be any change in internal energy?
No, sir.
No, and we can say that intuitively yes, कि यार ठीक है ना, कोई कोई टेम्परेचर का चेंज नहीं है, कोई फेज चेंज नहीं है, और केमिकल न्यूक्लियर रिएक्शंस तो वैसे ही नहीं हो रहे, पीछे क्या बचा. और यू कुड जस्ट कंसिडर कि वो आइडियल गैस लॉ, सॉरी आइडियल गैसेस के लिए ये डेल्टा यू इज इक्वल टू ये एम सी वी डेल्टा टी होता है. सो इफ देयर इज नो डेल्टा टी, देयर इज नो डेल्टा यू, राइट? सो देयर इज नो change in temperature, there is going to be no change in internal energy. ठीक है? So whatever reasoning you use, the idea is that there is no change in internal energy for the process 1 or 2, which means that Q12 is just going to be equal to W12. ठीक है? Which means that the heat transfer for process 1 or 2 is going to be equal to the same value over here, which is minus 160.9 kilojoules. ठीक है? So now let's objectively look at कि हुआ क्या है process 1 से 2 में. Process 1 से 2 में मैंने गैस को compress करने की कोशिश की है, और मैंने ensure किया है कि even though I am compressing it, I don't want it to heat up. ठीक है? इस compress करने में I actually had to apply work myself. The gas was not giving me any work. I had to do work on the gas. So hence the work done has a negative value. I had to do 160.9 kilojoules of work on the gas. And in order for it to not heat up, I had to remove the same amount of energy from it. मुझे उसे ठंडा भी करना पड़ा by the same amount, right? I had to remove 160.9 kilojoules from it by means of heat transfer so that it didn't heat up. ठीक है? So hence ये Q की value भी negative है, because this is not heat added to the system, this is heat removed from the system. ठीक है? So do the numbers and the signs make sense? कोई questions? So I'm going to assume that means no. So for process 2 से 3, work done तो हमें पता था, heat transfer पे हम बात कर रहे हैं. So once again, delta U is equal to, now it's Q23 minus W23, right? अब हमें इस process के बारे में क्या पता है? Is there any work done? Yes, there is. Is there any change in internal energy? Yes, there is. And what do we want to find out? We want to find this heat transfer, right? So there are two ways to approach this. एक तो ये कि मैं कहूँ कि Q23 is equal to delta U plus W23. ठीक है, and this change in internal energy is mCv delta T, right? And this work done for the process 2 से 3 was already shown कि क्या था, ये P times V3 minus V2 था जो हमने कैलकुलेट किया हुआ था ऑलरेडी। ठीक है, सो कुछ टाइम पहले हमने टेबल्स खोल के देखे थे।
सर ये MCP डेल्टा टी नहीं होगा?
एक सेकेंड में इधर वापस ये टेबल्स को मैं एक दफा दिखा दूं दोबारा से। ठीक है, सो ये CP और CV की वैल्यूज for different temperatures stated, but they don't change much if you look at them. So as long as we are not talking about really high temperatures, it's totally fine to just use the value जो कि room temperature पे होती है, जो कि ये वाली है। ठीक है, so unless I tell you otherwise, you can just use a constant value for ये CP और CV की। so इस सवाल में हमने ये जो है ना constant values इस्तेमाल करनी है। so going back here, देखें definition ये थी कि delta U is equal to mCv delta T, right? And delta H is equal to mCp delta T. जो आप कह रहे हैं ना कि प्रोसेस कांस्टेंट वो प्रेशर प्रोसेस है, तो यू आर एब्सोल्युटली राइट कि यू कैन जस्ट जो हीट एडेड ड्यूरिंग दिस प्रोसेस इज ओवरऑल इक्वल टू mCp delta T। ठीक है, बट दिस इज नॉट रॉन्ग आइदर। दिस इज stating के first law states के delta U is equal to Q minus W, which means Q is going to be equal to delta U plus W. The thing is, both of these are going to give you the same answers, and if they don't, we're doing something wrong. And you can actually check that on your own time as well. Regardless of which way you calculate it, ठीक है, यहाँ पे the numbers are going to be mass is 1, specific heat at constant volume is from that table that you just saw 0.718, mass के साथ किलोग्राम लिख लेते हैं, kilojoules per kg Kelvin, ठीक है, and delta T for the process 2 से 3 is basically T3 minus T2, ठीक है, so if you look up here, T3 is 1742 minus T2 is 348.4, right? So this delta T is 1732. I forgot. A second. 1742 minus 348.4. Obviously, this is in Kelvin. ठीक है, प्लस ये जो हमने ऑलरेडी कैलकुलेट किया था 500 multiplied by 1 minus 0.2. ठीक है, so of course if you want to add these two values, they both have to be in the same units, and we already know okay, this part, the second part, the work done was 400 kilojoules. क्या ये जो चीज है, क्या ये भी kilojoules में है? Very easy question. mCv delta
Yes,
T,
sir.
right?
Yes,
Kilojoule,
sir.
kilogram से kilogram कट रहा है, Kelvin से Kelvin कट रहा है, just this is directly in kilojoules, so you can just directly add them up. ठीक है, so let me just figure out कि कितनी है. 1 into 0.718 into 1742 minus 348.4 is 1001.6. ठीक है, so this is 1001.6, right? And अगर हम instead, if we just directly use this, it's going to be equal to 1 into CP की value once again from the table. I don't want to show it again, but I hope आप लोगों को पता चल गया अब तक ये table कहाँ से देखने हैं. Showed it a couple of times. The value at room temperature was 1.005 kilojoules per kg Kelvin multiplied by delta T is the same, यही 1742 minus 348.4. So once again ये kg में था और ये Kelvin में था, so the product is once again going to be equal gonna be in kilojoules, and it's gonna be the same number, which is around 1400.6 kilojoules. ठीक है? Make sense? I hope. All right, so the third process, ये heat transfer पे continue कर रहे हैं, was process 3 to 1, the isochoric process. और उस केस में delta U, this is still capital, is Q31 minus W31, but let's not forget कि isochoric process है, तो this was actually just equal to 0, ठीक है? And we pretty much know this कि, but we could have directly written this as well probably, is कि Q31 is just going to be equal to mCV delta T, ठीक है? So अब सवाल ये है कि यहाँ पे डेल्टा टी क्या होगा. हमारे पास दो ही ऑप्शन है कंसिडर करने के लिए, T3 माइनस T1 और T1 माइनस T3. कौन से वाला होगा?
Sir, second.
Yeah, it's final minus
T1.
initial, right? So it's gonna be 1 minus 3. ठीक है. अच्छा, बाय द वे, बिफोर वी डू दैट, अगर 2 मिनट इसको देख लें कि अच्छा 2 से 3 प्रोसेस में हुआ क्या है. 2 से 3 प्रोसेस में ये हुआ कि हमने कांस्टेंट वॉल्यूम पे एक्सपेंशन की, मगर इट डिडंट हैपन फ्रीली, राइट? उस एक्सपेंशन के नतीजे में वी गॉट सम वर्क आउट ऑफ इट, राइट? इफ यू लुक बैक एट द वर्क, 2 से 3 एक्सपेंशन के नतीजे में 400 किलो जूल्स वर्क आउटपुट हमें मिली, ठीक है? But it didn't happen on its own. We actually had to provide it a lot of heat. We had to provide it with 1400.3 kilojoules of heat, right? In order to achieve that, right? So we had to heat it up to keep the pressure constant.
सर समझ नहीं आपने सिर्फ क्या कहा है?
मैं भी ये कह रहा था कि प्रोसेस 2 से 3 को अगर हम जरा देखें ना कि हुआ क्या है. सो 2 से 3 में हमारे पास एक कांस्टेंट प्रेशर पे एक्सपेंशन थी, और उस एक्सपेंशन के नतीजे में वी गॉट अ वर्क आउटपुट ऑफ 400 किलोजूल्स, but it wasn't free. In order to keep the pressure constant, in order for this process to happen, we also had to provide it with heat. हमें इसे 1400 kilojoules of heat देनी पड़ी सिस्टम को, ठीक है? So that's what happened. We gave it 1400 kilojoules of heat. The system gave us 400 kilojoules of work, and we had a constant pressure process from 2 से 3. ठीक है? Right. So finally, isochoric process. जी, जो third process था, उसमें first let's look at the numbers. By the way, recall के work done तो 0 ही था. जो heat transfer है, that is 1 kilogram multiplied by 0.718 value of CV, kilojoules per kg, multiplied by the temperature difference T1 minus T3, जो कि 348.4 minus 1742 है, which is actually equal to जो हमने पहली वाली वैल्यू कैलकुलेट की थी ना, 1001 or something. It's just that part if you look at it, but it's also negative. ठीक है, 1001.4 या जितना भी था, 0.6 I suppose, I don't know, round off errors are possible. ठीक है. So what's happening here is के you're cooling it. आपने you're taking a constant volume, and all you've done is you've cooled it, and as a result of that cooling, the pressure decreased. That's all that happened. Volume constant रखा है, गैस को हमने ठंडा किया, प्रेशर गिर गया, right? सो यहाँ पे भी हम इसके जो वो है क्या कहते हैं, जो टेम्परेचर डिफरेंस है ना, instead of writing both of these in Kelvin, I'm asking, can I just use Celsius for both of these?
Yes, sir.
Yes, sir.
Yeah, so it totally works because you're taking a difference, right? जब तक आप कोई रेशो नहीं ले रहे या कोई मल्टीप्लाई सिंपली नहीं कर रहे, if you're taking the temperature difference, so it doesn't really matter if you take that in Celsius or in Kelvin. Alright, so we're going to call it here. I'm going to turn off the recording. अगली क्लास में हम बात करेंगे कि अच्छा इसका overall efficiency क्या है, what does that even mean? Any